Hey all. I want to give you a brief tutorial on STL files because I think there's a lot of relevance between an STL file and Calc 3 and 3D printing. So, STL files are essentially a universal file type that describes a shape in terms of a whole bunch of little triangles. And so right now you're looking at about the simplest shape I can make. So this is a tetrahedron. So this is four sided triangular faces, right? So I wrote this file by hand. So I'm going to show that to you. So STL stands for Standard Triangularization Language. And really what that means is that the file is basically just a list of triangles that make up a shape. So in order to determine a triangle in three-dimensional space, you need three-dimensional points. That's these three vertices. Then, in order to know which direction the triangle is supposed to be facing, you have a normal vector. That is exactly the same normal vector you're used to calculating in Calc 3. It is literally called normal in the code. Should be noted, STL files come in two different kinds. They can be either human readable or binary. This one happens to be human readable because I wrote it. Um, Binary ones are less human readable because they're made to pass triangles from a piece of CAD software to a slicer or something. Um, STL files are also generated by lots of other things. So CAD programs generate STL files. So do MRI machines. Um, so does LiDAR. Like, there's a whole bunch of things that are generated in terms of triangularization. So here's one of those, right? Um, let's look at this and look at our shape briefly to see what we're seeing. So this first loop, right? That's what this is called. It's the loop. Goes from the origin vertex, so that's 0, 0, 0, to the vertex at x is 1, y is 0, z is 0. So that's, we're going from the origin, we're going to go right 1, and then this third vertex is up 1, right? So that is this side that we happen to be looking at on our triangle. We're going from the origin here to the right and up. Should be noted when I'm hovering this, you're seeing 100, 100. I scaled this when I imported it. So this one is 100 millimeters by 100 millimeters as opposed to the 1 by 1 by 1 that it was when I imported it. So that's my first face, is this face looking at us. And in that order, so origin to x to z, if I think about wrapping my hand, origin to x to z, that's going to point my right thumb back out at me. And so our normal vector to that surface is going to be negative in the y direction. So if we look here, we're getting a normal that's just negative 1 in the y direction. So this other vertex here, right, or our second facet, we could eyeball where it is. It's down in the z direction for its normal. And then the vertices are 0, 0, 0, 0, 1, 0. So that's in the y direction. And then in the x direction. So that is our bottom face here. So we're going from the origin to the y direction back to the x direction. And indeed, if we circle that with our hand, we're going to get a vector pointed down. The down on this tells you what's inside and outside the shape. We could go through our other couple. It's worth noting this last one. They don't have to be normalized. So that normal vector isn't unit length. It's just 1, 1, 1. And that's from going here, we're going in the x direction to the y direction to the z direction. So looking at our shape here, that's x to y to z. And so if we wrap our fingers through that, we get a thumb pointed up and out. And that's that vector 1, 1, 1. That's the triangle, or that's the plane x plus y plus z equals 1 for reference. The others are the coordinate planes, right? This bottom one is the plane z equals 0. This one here is the plane y equals 0, and this one off to the left-hand side here is the plane x equals 0. So we know equations for all of our planes. We could easily find the points. This is how you write an STL file by hand. You just go ahead and chunk it in. It needs to have a little bit of formatting, so it needs the word solid and then whatever the name of the solid is, and then it needs an end solid at the bottom. Each facet needs to be a facet, which is made of a normal vector and a loop, and each loop is made of 3 vertices, each of which is made of 3 points. That's all there is to this. You can absolutely write your own STLs if you want. I would not recommend that, by the way. Writing your own STLs is very time consuming, probably not a great idea for a project. But I want you to know that these are in there, because I think it's really cool that everything you 3D print is just made out of little triangles stuck together. And when we're thinking about objects in our daily life, like this is just a spotlight I happen to have on the corner of my desk because we use it for the outdoor club. This shape, somebody went into a CAD program and used a whole bunch of calculus assisted by the computer to create this thing, right? There's like some parametric curve to make these little loops, right, that your fingers go into. And there's a formula for that curve. And then they extruded it, right? Like, they made that curve and then they extruded it in one direction. That's exactly the same thing we deal with cylinders, right? Along this curve, like all along this thing, there's all these little fillets. So a fillet's where the corner is kind of rounded. So all of those corners are rounded using some kind of parametric curve. There's a lot of calculus that went into making this, and nobody did most of that calculus by hand. Most of that calculus was done in the computer. But your goal as a calculus understander should be to look at things like this in the world and think to yourself, how did they make that? Where are the parametric curves in there? How did they do that? What did they rotate? Like, where's the center of mass of this thing? How do I think about this object in terms of the calculus I now know? Like, be surprised by the world around you. There's an insane amount of calculus in it. It would be really cool if you thought about this some. Thanks, guys. I'll catch you on the next one.